Hello, and welcome to my talk on statistical physics approaches to unique games. My name is Ewan Davies, and this is joint work with Matthew Coulson, Alexandra Koller, Viresh Patel, and Guus Rechts. The motivation for unique games is that it's an easy-to-grasp decision problem which takes place on a graph, and it has applications in proofs in hardness of approximation. It was conjectured to be NP-hard by Cott in 2002, and this conjecture has far-reaching ramifications in the analysis of approximation algorithms. If the unique games conjecture is true, and the unique games problem is NP-hard, then many approximation algorithms that we currently know are best possible, including the famous Germans-Williamson 0.878 algorithm for max cut, which is very interesting because if this were optimal, then that would be an indication that the geometry of the Germans-Williamson algorithm is somehow intrinsic to the max cut problem and not an artifact of the algorithm and the analysis of their algorithm. There are some results which suggest that the unique games problem has a different flavor to known NP-hard problems, particularly the sub-exponential time algorithm for unique games by Aurora, Barak, and Storer, which came out in 2010. So it really does seem to be the case that unique games could go either way. It would be very interesting to find out that unique games is NP-hard, but similarly, if the conjecture were to be refuted and a polynomial time algorithm given, this would likely lead to a number of breakthroughs in approximation algorithms and really be a significant advance. So, that the conjecture could go either way, and there would be impressive consequences in either direction. So let's define unique games. Like I said, this is a decision problem which takes place on a graph, but we have some extra structure. I need an alphabet, which for me will be the numbers 1 up to k, and a permutation of these alphabet letters on each edge of the graph. Formally, I'm thinking of the edges of the graph to be oriented so that you follow the permutation in one direction, you follow the permutation as stated, and if you reverse the direction of the edge, you follow the inverse permutation. This is a technicality which makes the definitions a little bit more convenient. It's not really intrinsic to the problem. So then we consider assignments of the alphabet letters to the vertices of the graph. So an assignment is just a mapping for each vertex in the graph. I have an alphabet letter. And the value of an assignment is equal to the fraction of satisfied edges of the graph, where a satisfied edge is one which, if I look at the value the assignment gives to the endpoints of the edge, I can get from one to the other, from xu to xv, by following the permutation that's on the edge uv. So that's a satisfied edge. Then the value of the instance is the maximum value of an assignment over all of the assignments, which would be k to the n assignments, where n is the number of vertices of the graph. So here I have 3 examples. The underlying graph is a force cycle, and I've drawn it 3 times. On the left is this the instance without any assignment considered. We just have a permutation on each edge of the graph. And here I'm considering the case k equals 2, so that I don't have to worry about orientations. Either the permutation is the identity, or it's the transposition which flips the alphabet letters. The next 2 pictures are examples of assignments and what these do to satisfy the edges. So in the first assignment, the middle picture, you can see that the top edge is satisfied because it's the identity permutation, and I see a 2 at both ends of this edge. And the identity permutation applied to 2 gives me a 2. Similarly, every other edge is actually unsatisfied, hence it's in a different color. And you can see this just by checking that, for example, on the right, the edge marked flip has 2 and 2 at the endpoints, but the flip permutation does not map 2 to 2, so that edge is unsatisfied. On the right, we have another example where I've given every vertex the label 1, and now 3 of the edges are satisfied. And if you go over all possible assignments, you could check that the maximum value of this instance is 3/4, where I've satisfied 3 of the 4 edges. I think the motivation behind the unique in unique games is that a permutation maps for every edge where I've already assigned a label to one endpoint, there's a unique value at the other endpoint which would satisfy that edge. So what is the unique games problem exactly? Well, like I said, it's a decision problem, and it comes with a couple of extra parameters. We're going to have the graph instance with alphabet size k, like on the previous slide, and 2 real constants, epsilon and delta. And we are told, when we're given this instance, that either the instance has value at least 1 minus epsilon, which I will call the yes case, or the instance has value at most delta, which I will call the no case. And then to solve the unique games problem is to correctly identify which of the 2 cases holds. Cott's conjecture from 2002 was that for all epsilon and delta positive, there is some k such that for large enough alphabet sizes above this k0, it's NP hard to determine which of the 2 cases hold. Let's just consider trivial algorithms for unique games for a second. There are exponentially many assignments, k to the n. So there's a trivial brute force search will tell you whether or not there exists this assignment of value at least 1 minus epsilon, which signifies the yes case. But we want a polynomial time algorithm to do this instead, which seems to be hard. The problem is intimately connected with approximation. As you can imagine, an optimization problem concerned with finding the value of an instance. And then if I had an algorithm which on some instance of value opt found me an assignment of value alpha times opt, then this algorithm could be used to solve certain kinds of unique games decision problems, provided I set the parameters up right. So I would need that alpha times 1 minus epsilon should be greater than the delta of the problem. The main, like I said before, the main motivation of the conjecture is improving inapproximability results, and there are many, many results of the form: assume unique games is NP hard, then the approximation ratio achieved for a certain problem by a certain algorithm is in fact optimal, and it's NP hard to obtain an improved approximation ratio. And the technical details in these proofs involve PCP constructions and long codes, but I'm not going to go into the applications of unique games here. I'm going to look at algorithms for solving the unique games problem. And there do seem to be relatively few existing techniques for unique games problems that give efficient algorithms. In particular, spectral methods have been applied to semi-definite programming relaxations of unique games, and this has led to the powerful approach of subspace enumeration. Here the idea is that by looking at the spectrum of the graph, and in particular the space spanned by the eigenvectors of large eigenvalues in the graph, these somehow span a space in which the near optimal assignments should lie. So you can obtain an approximation algorithm for unique games by brute force searching this subspace, which in some cases will be small enough to permit a polynomial time algorithm. So this gives an algorithm, say, for expander graphs, which have a very, very nice spectrum and only one large eigenvalue. And more generally, this technique led to a study of threshold rank, and it's a key part of the sub-exponential time algorithm for unique games, exploiting this spectral property of near optimal assignments. But our approach to unique games is completely different, and it's inspired by identifying a connection to statistical physics, which I hope to explain in the rest of the talk. We're motivated by the natural question of whether unique games problems can be made easier by strengthening the guarantee in the case of a highly satisfying assignment. That's what I call the yes case. So the point is, does the problem get easier if I guarantee there are many assignments of high value in this yes case? And it seems like such extra strength is hard to exploit with existing techniques, but our techniques can naturally take advantage of this, and weighted counting techniques from statistical physics perform very well in this area. So we define a generalized decision problem where an extra parameter f has appeared. So count unique games has a parameter f, and then a k and an epsilon and a delta, which correspond to a unique games instance of the type I described before. So we have a unique games instance with alphabet size k, but now the f parameter is strengthening the promise in the yes case, where I assume that I have at least f assignments with value at least 1 minus epsilon. And the no case is the same as in the original unique games problem. Every assignment has value at most delta. So let me just fix some notation for the rest of the talk. The constraint graph, or the graph underlying the instance, will be G with vertex set V and edge set E, and I will use N for the number of vertices. This is very standard. If you think about the definition of count unique games, then plugging in f equals 1, we get exactly the definition of the unique games problem. So this is a strict generalization. And again, if you think about f equals k to the n, this is all of the assignments. So in the case f equals k to the n, the guarantees in the yes case and the no case both cover all of the assignments. So provided the problem is well posed and 1 minus epsilon is bigger than delta, I can solve the problem by checking an arbitrary assignment, and the value of that assignment will tell me which case must hold. So for f equals 1, we have exactly unique games, and for f equals k to the n, we have a problem which is trivially in P. This raises the very interesting question of whether there's a threshold in this f parameter where, for small enough f, count unique games and unique games are equivalent, and as you raise f, they remain equivalent for some time, and then there's a point at which they become inequivalent, and then count unique games is in P. So this is a landscape that might be possible to prove if the unique games conjecture is true. Of course, if the unique games conjecture is false, then we might expect count unique games to be solvable in polynomial time throughout the entire range. So we've just introduced a slight generalization of unique games, and as you'll see, our techniques motivate understanding how this problem changes as f changes, because it's intimately connected with the limits of the methods that we have right now. It is worth noting that if you take a unique games instance, if it's in the yes case, then you can modify a small number of the labels in the optimum assignment to get a near optimum assignment. And because you can do this in many different ways, you might expect that a unique games with a single highly satisfying assignment has quite a few, nearly as highly satisfying assignments. And plugging in some parameter values, you can show that from a unique games instance, you can get a count unique games instance with exponentially many in n assignments, where I've slightly degraded the epsilon parameter by this constant factor 3. So this sort of simple argument motivates studying f parameters round about k to the epsilon n, because already for f smaller than that, count unique games should be equivalent to unique games. So let's introduce some of the statistical physics that we used to give the problem and give a new solution to this count unique games variant of unique games. I'm going to use some language which is standard in the statistical physics community, but I'll explain everything as I go so that the talk will be self-contained. So we associate to each unique games instance a partition function, zgw, which is just a polynomial in w, and the coefficients of the polynomial depend on the graph and the assignments, and this is exactly what we're going to use to solve the problem. So the definition of zgw is that given any assignment, we count it with a weight w to the power the number of satisfied edges in that assignment, which by my definitions is the value of the assignment times the size of the edge set of the graph. And For the purposes of the calculations that I'll give on the slide, it's useful to think of W being a real number, at least 1. However, for our proofs, it is important to consider W being a complex number. So deep in the technical details of the proof, complex numbers arise, but we're most interested in real W when it comes to applying the techniques to solve unique games problems. So, according to the definition I gave, here is a sum which gives ZGW, and the key observation is that now, when W is a real number, at least 1, the two guarantees of the unique games problem, the yes case and the no case, give contrasting bounds on the value of this partition function, which remember is just a polynomial. So in the yes case, we have at least f assignments with value at least 1 minus epsilon. So if I just consider the terms in the sum, which come from those highly satisfying assignments, I get a lower bound on the partition function. Secondly, in the no case, every assignment has value at most delta. So provided I put in a k to the n here corresponding to every assignment, I'm upper bounding every term of this sum by w to the delta times the size of the edge set, which gives me an upper bound on the partition function. So if w is carefully chosen such that these two intervals are disjoint, then knowing the value of the partition function helps us solve the count unique games problem. And here you can see immediately that larger f makes the problem easier because it will push these two bounds further apart. So this is where the count unique games formulation naturally arises when you transform unique games into a statistical physics question about partition functions. If you think a little bit harder, then you'll observe that it suffices to have an approximate value of the partition function. And this is important because, generally speaking, partition functions of this type are sharply hard to compute exactly. So we want to avoid requiring any exact computations of partition functions in our methods. So a more precise version of the discussion I gave on the previous slide is the following lemma, which says to solve some count unique games instance where, for simplicity, I'm assuming that the underlying graph is d-regular, so every vertex sees d edges. It suffices to obtain some approximate value xi for the partition function, where the approximation guarantee is that the ratio of the two numbers is bounded by e to the cn. Again, n is the number of vertices of the underlying graph of the instance, and c is just a constant here. Then you can do some computation to show that provided your w parameter is large enough in terms of all of the other parameters of the instance, then knowledge of xi is sufficient to solve the count unique games problem. And our paper is about applying two techniques from statistical physics to the problem of approximating this partition function. Both of these techniques are concerned with approximating the log partition function by evaluating a truncated Taylor series around the special point w equals 1. If you think back to the definition, at w equals 1, I'm giving the same weight, exactly 1, to every single assignment in the sum. And so the partition function is trivially equal to k to the n. So somehow w equals 1 represents an easy point, and we use a Taylor series around this point, which we understand very well, to obtain approximations of the partition function for larger w. So the first theorem we prove has the following statement. Given some epsilon and delta such that the problem makes sense, and some fixed number of colors k, then for a large enough degree d, we can solve d-regular count unique games instances in the stated time, provided this f parameter is at least k to the 1/2 plus epsilon plus delta times n. So by the previous discussion, this is sort of vaguely in the right area for f. You know, we're not demanding k, f be like, it's significantly less than k to the n here, because I've got a 1/2, k to the 1/2 n is the sort of main term in that lower bound on f. And then if you look at the running time, provided, say, d and k are constants, this is in fact a linear time algorithm. And the key technical step in the proof of this theorem is to show that there is some region U in the complex plane containing this special point W equals 1, such that the partition function is non-zero in that region. So we call this a zero-free region. And if that's the case, an appropriate Taylor expansion for log partition function can be shown to converge, and then it's a matter of determining, the largest W parameter for which you can prove this Taylor expansion is convergent. That essentially determines the lower bound on F in this theorem. We have a second theorem proved using a different method, which again, for the same epsilon and delta conditions, says that when D is large enough in terms of epsilon and delta, and provided K is large enough that log K is bigger than D to the 3/2 log D, we can solve D regular count unique games instances. But this time, the lower bound on F is just K to the 2 epsilon plus delta times n. We've lost this additive factor of 1/2. Now this is much closer to the sort of range where if we had algorithms for F a little bit smaller than this would be strong negative evidence for the unique games conjecture. Again, it's best to think of K and D as constants, and then we have a polynomial time algorithm here. The lower bound on K is an artifact of the cluster expansion method that we use to prove this theorem, which is also based on Taylor expansion, but it's sort of more closely related to the multivariate Taylor expansion of the log partition function. Like I said, if we could prove such a theorem with F just a little smaller, say K to the epsilon over 4 times n, there's an n missing on the slide there, this would be strong negative evidence for the unique games conjecture, because it would be giving a polynomial time algorithm for certain classes of unique games instances. So I'll just say a few more words about the statistical physics behind what we're doing. From the right perspective, unique games problems are about approximating the ground state Hamiltonian of a statistical physics model. And that's the model given by this partition function Z, which we defined in this work. Usually in physics, the ground state Hamiltonian is a trivial object to calculate. The person who sets up the model knows exactly what the ground states will be and what their Hamiltonians are. But then the questions you might ask in statistical physics are typically much more precise approximations of the partition function that do require rich knowledge of the graph and the statistical physics model involved. Our proof of the zero-free region is rather hands-on and has a lot in common with complex dynamics as we study iterates of a function, and what we want to do is set things up so that we have some function, and provided iterates of this function don't reach certain points in C, our partition function for the model, Z, will not reach 0. So there's some conceptual leaps involved there, but underlying the proof is some interesting connection to complex dynamics. And for theorem 2, where we use the cluster expansion, the proof we can write down is more straightforward, as there is a sufficient condition for the convergence of the cluster expansion, which is frequently used in the literature, called the Kotechi-Price condition. In fact, there are several conditions of this type, and verifying these conditions is usually somewhat straightforward, and a lot of the work has gone into proving that the condition is in fact sufficient. So that somehow hides a lot of the technical complexity of the proof. Theorem 2 is also nicer because the resulting bound on F was quite a lot closer to the very interesting range where we'd be starting to solve original unique games problems. Lastly, I just want to discuss some interesting ideas for future research based on what we've done. So again, a little more statistical physics language. If you consider the special case of a unique games problem where you have the identity permutation on every edge, then the partition function that we used corresponds exactly to the partition function of what's called the ferromagnetic Potts model. This is a sort of multi-spin generalization of the well-known Ising model, which is used to model magnetism. And for this ferromagnetic Potts model, there is some sort of barrier at W equals 2 minus little o1 log K over D. And this barrier is observed in statistical physics as the order-disorder phase transition. Now this particular W is quite interesting because if you recall back to the earlier slide, just above, some constant factor above 2 log K over D is right, the type of W which we would want to be using to solve unique games problems. So somehow just beyond this barrier is the very interesting parameter range for count unique games. So then there's an interesting question of whether we can devise techniques for the problem which don't hit this sort of the barrier. You know, there's some underlying details of the model which change at this order-disorder phase transition, and it's a big open question whether they really affect what's going on in the unique games problem, or whether this is some statistical physics phenomenon which can be handled. Like I said, results analogous to ours just beyond this barrier would be strong negative evidence that unique games in NP hard. Using the cluster expansion, which we used for theorem 2, to obtain algorithms beyond such barriers on special graphs for similar problems, although with slightly simpler partition functions, is a very recent development. So there's been recent algorithms for approximating partition functions on lattices and expander graphs, which work throughout the whole range of W and don't observe this order-disorder phase transition and any difficulties that that introduces. The point is, such difficulties can be managed on special graphs. It's very unclear whether this can be applied to unique games for fairly difficult reasons relating to ground states and the underlying statistical physics models. I think it'd be very interesting to exploit graph structure somehow with our approach and obtain, for example, a new algorithm for unique games on expanders. There's good evidence that unique games is easy on expanders from previous work. And on the statistical physics side, there's also evidence that expansion can be put to good use in the approximation algorithms of the type that we've discussed. So I think it'd be very interesting to push this project further by managing to combine, you know, these two things: the knowledge that unique games is easy on expanders, and the techniques from statistical physics for approximating partition functions on expanders could be combined to push our results further. That's all. Thank you very much.